Alright, let's get started. Here we have this formula of the discrete Fourier transform, and I rewrote it as the following, as these two terms combine. What I did was simply using a little bit of algebraic trick, like making it 2n plus 1 and 2n instead of just n. And I cut the capital N in half, so that now this term will take care of the odd number, and this term now will take care of the even number. So the formula itself is unarguably the same as these two terms combined, unarguably. Okay? Also further, we need to factor this one out. We need to rewrite this term. Whenever we see a term in the form e to the 2 pi over capital N k times a parenthesis, inside the parenthesis we have something n plus something. We need to factor out the something out. That's the constant. The steps are shown here. Since this is the same as this, and we factor this one out. K here at this point is just a constant. This is a summation of n. Also, these things that I factor out are actually what we call the tutor factors. They are the keys to the fast Fourier transform. Let me, in the rest of this video, just call them tutor factor. Alright, let's look at what I did here on the right. What I did here on the right was just simply breaking down those terms that have no tutor factors further and further into smaller and smaller summations, as you can see here. But why did I only break down the terms that have no tutor factors? What about the terms that have tutor factors? Can I break them down? The answer is yes, we can definitely break them down individually. But it turns out that if we just substitute the terms that we got from the terms that have no tutor factors, and we substitute it into the terms that have tutor factors, like these two terms into this term, and this whole thing into this term, and we'll get the same thing. We'll get the same thing as we would break down all the terms individually. Since this term that has no tutor factor and this term that has the tutor factor, their e to the 2 pi over capital N something is the same as each other. This part is the same as this part. You can confirm it by breaking them all down individually. But I want to remind you that if you try to break down the terms that have the tutor factors, remember, you have to put the tutor factor, like this tutor factor, back inside the parentheses, like changing it from this form back into this form, and then look at these numbers and try to break it down algebraically. If you just look at this number, you look at it in this form and try to break it down, you will get the wrong answer. Okay, let me start to use W as the notation of e to the 2 pi over capital N. Okay. Remember I said earlier that if we substitute all the terms that have no tutor factors into the terms that have the tutor factors, we'll get the same thing as we would break down all the terms individually. We'll get the formula in the right form. And we'll get many same terms everywhere, many same operations everywhere, but done with different x of n. Okay? The x of n, of course, need to be changed as indicated here. Okay? The x of n's are the amplitude of a data point. Okay? Now let me tell you what will actually happen when capital N is equal to A. If capital N is equal to A, you see these two terms on the bottom, they'll just be a number. Since if capital N is equal to A, it's just 1 minus 1 equal to 0. So this summation is just 0, n equal to 0. So when n is equal to 0, it's always w to the 0, which is just a vector aligning on the real number line. It's just 1. So it's always just x of n. Everything in the first stage always starts as a vector that's lining on the real number line only. But as we proceed the calculation, we get the tutor factors to rotate everything around, and eventually we get to the final stage, the answer. We get everything right in the end. Let's just see what's geometrically happening. Okay, this is what is geometrically happening. As you can see, we have 4 of these 2 terms on the bottom. Every vector that we start with, like this one, this one, this one, this one, this one, this one, all these, they all start as a vector that is pointing to the right on the real number line with no imaginary component. And in each group, one of them will get multiplied by a tutor factor and hence rotated, and then combined with another. Another will stay the same. And then we just recursively combine all of them. But at each stage, always, half of the vectors will get multiplied by a tutor factor, and another ones just stay the same. And by doing this step by step, we get to the right order. In the end, we get everything in place. This is the right order when k is equal to 1. If k is not equal to 1, like say it's equal to 2, then the order will be very different. Like this one will goes here, and this one will goes here, and this one will goes here, and this one will goes here. It'll be very different. Also, these vectors that are shown here, they don't all have the same length. They have the length x of n. Okay, the x of n is the length of this vector. Okay. Also, the vectors of the vectors here are actually not kept separate while we are combining them. Whenever we combine a group of vectors, we basically add them up already. We add them up by vector addition. Since if we rotate a group of vectors and then add them up, we'll get the same as we just add them all up and then rotate it. In the end, we have to sum them all up anyway. That's what the discrete Fourier transform tells us to do. Okay, let me now introduce to you what the butterfly diagram actually is. Look back at this picture. If we now know that this formula can be seen as a function of k, then I'm going to say the butterfly diagram is just a very efficient method for calculating this function of k for capital N times, for all possible k. The reason the butterfly diagram is so efficient is actually because it utilizes the rule of unity of these tutor factors, like this one, this one, this one, w to the k, w to the 2k, and w to the 4k. Let's look at what these tutor factors actually are and their rule of unity. Okay, these 3 circles and the vectors are showing you the rule of unity of these 3 tutor factors when capital N is equal to A. They basically show you all the possible outcomes, like these vectors are the possible outcomes of these tutor factors for any possible k, like all the possible outcomes that each of these tutor factors can repeat. They will repeat themselves as k goes on, and it's just because they are going around a circle. Let's talk about the butterfly diagram again. From the last part of the video, we know that there are actually not many possible outcomes for each tutor factor. And they repeat themselves. They repeat themselves as soon as they finish going around one circle, one full circle. And each stage, we have only 1 to the factor. Now, is there any idea that come to your mind? There's actually something crazy that we can do. We can literally list all the possible outcomes of each stage and reuse every single result that we already have in the current stage to calculate the next stage. This way we are sure to save ourselves tons of work. And this is exactly what the butterfly diagram will do. The butterfly diagram is a method that we can see when we look at this formula of the discrete Fourier transform in the form of this, in this broken down form. That is basically it. Finally, we are here with the butterfly diagram. In the last part of this video, I said that the butterfly diagram is actually listing all the possible outcomes of each stage. And it is what it looks like in action. I will explain the detail of it later. Right now, I would like to first explain how to look at this butterfly diagram. You see all these lines, they're just addition, like vector addition, complex addition. Okay, and these two factors that are on the lines, they are complex multiplication. It means if you want to add something to this, like add this x of phi to this combination, this x of phi will need to be multiplied by this to the factor first before it is added to this combination, this point here. Now some of you might say, hey, this is not the butterfly diagram that I know. The butterfly diagram that I know has many negative one on some of this horizontal line, like this one, this one, this one, this one, this one, this one. And many of the point itself actually gets multiplied by a to the factor. Not like this, going in different direction, multiplied by different to the factor. Not like this at all. But I would say it is actually the same. Because each of these two to the factors, like these factors and this to the factor, this factor and this to the factor, each of these two, they're the exact opposite of each other. Like not conjugate, but opposite. Like this one multiplied by -1 is equal to this one. W to the 6 multiplied by -1 is equal to W to the 2, and vice versa. So they are the same. It makes perfect sense that you multiply this point, this combination itself by this first, and then when it goes this way, it stays the same, but when it goes this way, it multiplies by -1 to obtain that opposite stuff. The reason I wrote them down in this form is just to show you that the butterfly diagram has the same structure as the formula that we discussed a lot earlier. The same thing, the same principle. Okay, let me first tell you how to obtain the order of these x of n. As you can see, they are not 1, 2, 3, 4, 5, 6, 7. Let me just first explain how we get this order. Okay, the method of placing the x of n in the right order is just this thing on the left. It's actually a lot simpler than it looks. Let's just do an example, okay? Assume that capital N is equal to 16. And according to this method, the first one is always 0, no matter what. And then the second one, the second x of n, is always capital N over 2, which is in this case is equal to 8. Okay? And then we're going to find the neighbor of this group. This little group, only two terms. Okay? The neighbor of this group is always the group itself added with something else. Alright? It is capital N over 4, always. And capital N over 4 in this case is 4. So we added with 4. Here, and 12. And then we are going to find the bigger neighbor group of this group. The bigger neighbor group of this group is still just this group itself added with something else. And it is capital N over A, okay? It has to do with the to the factor. I will explain it later, okay? 16 over, okay, we add 2, so we get 2, 10, 6, 14, 4. Am I running out of space? Yes, I guess. 8 and 16. Okay, just like this. This is the right order. Okay, now let's use what we already know to reconstruct the butterfly diagram. To reconstruct the butterfly diagram, we simply just need to list all the possible outcomes of each stage, as I have mentioned, okay? And to do that, we need to first look at these 3 tutor factors of each stage. Also, these terms and points that I put inside a box are the things that will later get multiplied by a tutor factor at each stage, while all the others will stay the same. Okay? This is just the structure of the formula. The formula that we saw earlier just worked this way. Okay? Now let's look at this first tutor factor of the first stage. It is w to the 4k. When capital N is equal to A, it will only give 2 possible outcomes for any given possible k, okay? So if it only has 2 possible outcomes, then I can just assume k go from 0 to 1. Since if k is equal to like 2, it will be just the same as k is equal to 0. It will start to repeat itself already. Now let's assume that k is equal to 0 for this point, or this outcome of this stage, okay? When k is equal to 0, this tutor factor gives w to the 0. So I'm going to multiply this term that's in the box by w to the 0 and add it to that point, okay? And then also, for this term that has no tutor factor, according to the formula, according to the structure of the formula, we will just add it to this point as well. Okay? Later also this point. Now next, assume that k is equal to 1. When k is equal to 1, this tutor factor gives w to the 4. So still this time, also this term multiplied by the tutor factor w to the 4 and added to it. And then also this term. Now for all the rest, we can just do the same thing. I mean, we can just copy these lines and the tutor factor for each 2 of them, okay? Since according to the formula, it is just the same operations done everywhere, but with different x of n, okay? At each stage, it is similar. Now in this next stage, we have w to the 2k. It is a different tutor factor, and this tutor factor gives 4 possible outcomes. So this time I'm going to assume k goes from 0 to 3. Okay? Assume that this point, this outcome is k equal to 0. And now I need to find out which 2 of these 4 points, or you can call them the 4 outcomes from the previous stage, which 2 of these 4 I need to add to this point. Okay? Now let's look back at the previous stage and ask which 2 are k equal to 0. Well, apparently it is this one and this one. I said it earlier. Okay? So let's add these 2 to this point. Of course, this one that's in the box will get multiplied by the tutor factor given k is equal to 0, okay? So it's w to the 0. Now next, assume that k is equal to 1 for this point. In the previous stage, k equal to 1 are these two. Okay, so I'm going to add these two to this point. Also, this one get multiplied by the 2 factor given k is equal to 1. It is w to the 2. Okay. Now what about when k is equal to 3? Well, when k is equal to 3 in the previous stage, it's just the same as when k is equal to 0. Alright? I said it earlier also. So I'm going to take these two. K equal to 0. Yeah. But this time it's gonna be this one that is in the box is gonna be multiplied by a different factor given k is equal to 2, and it is w to the 4. W to the 4. Now at last, assume that this points k equal to 3. Well, in the previous stage, if k is equal to 3, it's just the same as k equal to 1. Yeah. So these two again. But the 2 factor will be different. W to the 6 this time, yeah. Okay, now for the bottom is the same thing. Just copy the same thing. Same operation, both sides, done with different x of n, okay? Okay, now finally, in the last stage, we have this 2 factor w to the k, okay? Since it's w to the k, basically we have to assume k goes from 0 to 7. Or in any case, 0 to capital N minus 1, okay? So first, let's assume that k is equal to 0. When k is equal to 0, in the previous stage, apparently these two, okay? Of course, this one again multiplied by the 2 factor. It's w to the 0. It's just k, w to the k. And then for 1, it's the same thing. Of course, this one, these two. And w to the 1, yeah. K is equal to 2, k is equal to 3, k is equal to 2. W to the 2, yeah. And last, k equal to 3. So w to the 3. What about when k is equal to 4? When k is equal to 4 in the previous stage, it is the same as when k is equal to 0. Alright? It's just a rough unity. It repeats perfectly. So these two. Of course, it's gonna be multiplied by the different to the factor. Okay? It is w to the 4, yeah, of course. Then the same thing. When k is equal to 5 in the previous stage is the same as k is equal to 1. This time it's w to the 5. Oh crap. Same thing. This is just how we do it. W to the 6. And finally w to the 7, yeah. Basically, this is just how we do the butterfly diagram, intuitively. As long as you know what you are doing, I don't think you can get lost that easily.